The chat windows. Okay. So yesterday we have talked about a few things, and I said that I would be covering on this ASIC design flow. So okay. So I believe everyone is familiar with the design flow. Bit louder. Okay. Is it okay now? Or I think I just adjust my microphone. I just stuck it in my. Okay. Is it better?
Yeah,
Okay. So yesterday we have talked about ASIC design flow, and I would be explaining more on it. But I will again, I will not cover, in a very deep manner, but definitely I will give you a good idea that what you understand by a design flow, and what are the different stages of design. Yesterday we talked about that it is divided into three parts. That is front end design, back end design, and the foundry side. Okay. So when we say that, okay, what do you front end design? The front end design is that where it is only you are concerned about the front face of the design. For example, how the remote will function, like how many buttons would be there, what kind of operations it will perform. Because yesterday, you remember we took an example of Amazon, that Alexa remote for the Amazon Fire Stick, which is a voice operated remote. So you are just focusing on that. Okay, what kind of features the remote will have and how it will function, what kind of features it will offer. Okay, so once that has been finalized and tested, so you move it to backend design, where it is you are more concerned that how it will be executed in the real world. So also we took another example of designing or fabricating, or you can say a manufacturing or erecting your own house. So while at the planning stage, that how many rooms you want or how your house will look like, etc. So that is all the front end part. So once you start erecting the house, then you go to back end design. Okay. So now let's take the front end design part. That what do you mean by design entry, and what are the different stages of the design, and how you understand them. So design entry, it implies that you are able to describe your system. How do you model it? For example, you are trying to make your own house. So you have to first design it. So how you do it? So either you take a blueprint where you make the sizes of your rooms and everything like this on the paper. You are designing it, or you are using a 3D softwares, and on a desktop computer you are trying to make the design entry. So how you're describing it? Okay, so it's just like, for example, for simplicity, I take an AND gate. So you want to describe this AND gate. So how you do the design entry? Either you make an schematic that, okay, there would be one input A, one input B, and the output would be called as Y, and these are my IOs. This is how my schematic will look like. So this is my schematic design entry. Now this can be also possible that uh, you are writing in VSDL. So you say that Y is nothing but A and B, simple. Okay. Or in Verilog, you may write that it's A ampersand B. So this is how you want it. So this is nothing but the description of the design. So this is called a design entry. Okay. So once you do a design entry, the design is converted, okay, into a gate level netlist by a process known as synthesis. So synthesis is a process by which you convert your design entry to a gate level netlist. Netlist means it is interconnection of the components, okay, or it is like uh, conversion of an higher level description into a lower level description. Okay. Now, if you just note that the input to the synthesis block are two. One is your design file, which needs to be synthesized or converted, and another input is your technology library. Okay. So what do we understand this? So for example, you wrote this statement that why is nothing, this is the function you want to have, which is a simple AND gate. So this is how you have described it. Okay. This is your design entry. Now there is something which is called as technology library. Okay. So in my technology library, I have these components. I have a NAND gate, a NOR gate, yeah, multiplexer, or maybe an inverter. So these are the components only I have in my library. Now you tell me that how the design would be made into an AND gate. Okay. Shall I put chat window side by side? Okay. Let me just have the chat window so that in case someone puts up a question. Yeah. Is it audible now? Because I just saw one message a few minutes back. Uh, there's a disturbance. Okay. Just hold on. Maybe I just there is a fan nearby to my cabin. I just get it turned it off. Okay. Uh, is it getting better? The voice quality and the volume, is it okay? Okay. So we are talking about that how this AND gate would be converted. Okay. How this AND gate would be made using two NAND gates. That's great. Yes. So the design may use this thing. We will put this. Okay. And okay. That's it. So this would be my AND gate, right? So he'll just invert both the inputs and NAND it again, and tada, you will have your AND gate. So this is nothing but your synthesis process. This conversion of this description into this netlist, or into this design, is nothing but a synthesis process. Okay. So if someone wants to remember these components, this is what the components we have. These are the components we have in our library. So if I just make it white, and someone wants to use a NOR gate, okay, in the technology library file, you have only NOR gate. So probably he would be again doing the same. He would be just inverting the A input. He would be inverting the B side, okay, and then okay, just ignore the drawing errors, but I believe you guys are getting the major part of it. Okay. So this is how it would be. Instead of NAND gate, I would be using NOR gates, because in my library, this is what I have and this is what is available. So this is what the synthesis does. He converts your design entry into a netlist. Okay. Netlist means like it is interconnection of the components, because let's say there were 3 AND gates. So this is how he will write in text, because this is what the computer understand, that this is the AND one. So there is input A, and the second input is also A. The output is, let's say, temporary output, which is called as T. Okay. And the second component, he will write the second AND gate. He will say B, B. Okay. Because as it is recording also, so my screen is not running good. Okay. Okay. So it will be T, comma Z. Can you understand this? So this is just a simple text file. I can describe this in. So this do not looks like a schematic. It's just a simple text file. You can write all these 3 values, and you will have your netlist. So this is what the software does. This he converts your design entry into an gate level netlist. Okay. So once you do this, you go for the STA, that is static timing analysis. You try to find out that at what is the maximum frequency at which your circuit can operate. So I believe so because of what is the maximum frequency you can operate. Okay. So this is the job of the STA. How do you find that? I believe everyone must have seen products in which they mention and label that this is the maximum operating frequency of the circuit, or it can work at 1.9 gigahertz, or it can work in 2 gigahertz. So how they find it? So this is what the STA does. Okay, so it's a simple logic that if you have these gates, and if you have delays available in your library, because these are constant. I mean, if you say the delay of this gate is 2 nanoseconds and the delay of this gate is also 2 nanoseconds, so obviously this will also be 2 nanoseconds. So the delay between A to Y is 4, and B to Y is also 4 nanoseconds, right? Or whatever the time unit is there. So you can just simply find out, okay, this is your maximum delay. So at this speed, my circuit should operate 4 nanosecond. Because if you try to work faster than this, because if you make any change from 0 to 1, so output will go respond to this after 4 nanosecond only. So if you are applying input faster than this, so probably you will not get correct outputs. Okay, so it will be giving a false outputs. So that is not good. So that's why you do STA, and wherever you find that your design is not operating to your desired timing results or timing performances, you can always redraw or redesign the system. Okay, again. So the timing libraries, these are the library for where all the delay factors are stored, information is being stored over here. Okay. Then you have the next stage, which is module partitioning. So then you again divide that, okay, which segment of the design would be clubbed together, grouped together, so that they are connected in the shortest manner, and they will not disturb the nearby zones, etc. So based on this partition, actually you move out to the backend part and you design the floor planning. So floor planning is that, okay, how much amount of area is being provided to you on the silicon, and you partition the entire system and decide that, okay, which block should be placed close to each other, so that there is an fastest performance you get and the best packaging of the transistors possible at the lowest power. Okay, so based on all these constraint factors, so you do the floor planning. So generally the softwares are there which help you to floor plan the design better. Okay, so but it is the designer who has to think on partitioning, because till now the softwares are not that smart enough to decide, okay, shifting of the components to different sides or corner, or the geometry of the chip will produce what kind of results. Okay, so once this has been done, floor planning, you move out to layout compilation, where actually you convert the gates or every transistor into a given format. Okay, because for example, if you had this NAND gate, okay, so how the NAND gate is being laid out, it is laid out in an like, you know, vertical format. So you have a rectangle like this, or the geometry of the gate is like this, or it is in the horizontal format, how it is. Okay, so it depends. There are 2 3 varieties available of each transistors or a gate formation, so that they can be fitted nicely in a given area. Because let's say this is your chip plan, and only this much side is available to your block, so you cannot fit in a horizontal design, isn't it? Then you can say that, sir, we can rotate. Yes, you can rotate, but instead of rotation and giving some problems on the pad locations, it's better to design first and validate that after rotation they will work nicely. So the pre-configured cells are available, which are available in this format. Or let's say you might be having a chip design like this, and only maybe this much area is available to your packaging, okay, of the gate. So if you can design something like this, yes, this is one, then this is another one, and this is another one. Okay, the third one. Okay, so you can see that this guy is not in the straight format. So this is what the layout was available. Okay, so these are different combinations are available. So based on the physical library input, the layout is generated, and when it's being generated, it is placed and routed. That means it is actually placed in the silicon, not in the reality, I mean, but in the softwares. And you do the routing, that is interconnection of the component based on the rule files. The rule files, I would be talking about it. In the next coming few slides, we will be talking about design rule files. And you can do the cross section. The cross section analysis that you check in the 2D cross section or three-dimensional view, and you have a look on the entire design that if if there is any possibility of any kind of errors or failures during the fabrication. If there are possibilities, then you try to rectify them and try to sort out all the issues which might be popping up during the fabrication. Okay. In between, you have a big chunk in the flow which is called as simulation block, and it is being applied at the different stages of the design. So the first one is the function simulation. That means once you do the design entry, you validate that will my design work properly functionally or not. So that means if you are planning to make an AND gate using NAND gates, will it work or not? I mean, will there be any problem or something which will be not acceptable? You can just quickly validate. So here, the timing performance is not important. The important is only and only about the functionality of the design. But after the STA, that means once you reach to STA, then you can go for the pre-layout simulation. So that means you just check that, yes, I wanted an AND gate whose delay should be less than 3. Okay. But I have made an AND gate using the NAND gates. So here I am getting a delay of 4. So it might be acceptable to you, it might not be acceptable to you. So you have to decide on that. So ST will let you know that in this design, the delay is 4. Is it okay to you or not? If it is not okay, then probably you have to change the library which you're using. Okay. Or maybe get that cell which you specifically require for doing this purpose. Okay. And the third simulation comes up after the place and route. Okay. So after you do this all job, you come from here to over here. So in post layout simulation, you not only validate the functionality of the design, but this time you also take care of the delays in between. So because as you are using a gate design like this, so after the layout, here the delays were like this. Okay. So the total delay was earlier coming 4 after the STA. Okay. But after the routing, the delays of these interconnect wires in between, they might also play a role. This might be like zero point 0.2 and this might be zero point 0.3, something like this. So now the delay of this side is 4.3. Sorry, excuse me. So this is the slowest path, B to Y. Okay, so based on this, uh, your computations will change and the functionality might be affected. Okay, because you are applying the input at the 4 nanosecond, but the delays in reality are 4.3 after the routing. So that has to be taken care of. So that's why simulation plays a very important role, stage by stage, validating the design will work properly, not only functionally, but also with the timing requirements. Okay. So once you move out, you go to the foundry side where this is the job of the fabricator, that he makes sure that whatever the descriptions you have made in the software design files, they are matching with his toolkits or the fabrication design kits which he's using it. So the kind of materials he's using, the properties which have been applied in the software, they are properly as per his standards of the factory. So based on all this verification and of the description of the materials, the fab sign off happens, and you just give a green go flag to the fabricator that yes, you can go for the prototyping, uh, and once a prototype is validated and functionally okayed, then you can go for the mass production. Okay, so this is just a general overview on how the design flow happens. So let's today move out designing our own IC, that is using CMOS MOSFET transistors. Okay, so designing CMOS ICs or layout is not that complicated. It's very simple and easy to use and to understand. Okay, so generally they are made using stick diagrams, or you can say something, some kind of block set, you can say, or some kind of rectangles, you can say. They are used to make the design. Okay, so you have color code for every layer. I will be explaining the structure of the colors and the structure of the different layers as the time permits. Okay, so these blocks are made using a grid which is called as either lambda grid or the micron grid. So micron is working on lambda grid. Okay, Lambda grid is lambda is just a factor which is half of the technology. Okay, so the grid used by the microwind is lambda. Okay, and is generally half of the technology. And for example, if you are using a 90 nanometer technology, okay, then lambda is 45. If you are using let's say 14 nanometer technology, so lambda would be 7 in microwind. Okay, 7 nanometer. So what does this mean? This means that the grid which is there in microwind, okay, so this is lambda. So every unit this by this is lambda. Okay, I believe everyone is clear about this, because this is very important, that how the grid is being made, and how microwind processes lambda. Okay, so it's very simple concept. Okay, let's move further. I would be making so if you want to make an NMOS transistor, this is how it looks like. Okay, so you have a green block at the bottom side. This is a green block. On top of it, you have a metal layer which is of blue color. So the square kind of blocks you see, these are the contacts or the vias which connects the metal layers to the diffusion layer N type. On the middle one, what you see is then red block, that is a polysilicon or the gate material. Okay, and all these units have been made in microwind, and probably it'll be good I just show you one practical uh, making of it. Okay, I just open my microwind software. Okay, no need to follow through. Don't open your software and start following it, because you will miss the point. Okay, don't follow through, because the videos are available on my YouTube channel, and uh, you can record. You will get the recordings. Okay, don't worry. So I take some old technology so that it's much more simpler and easier for me to explain. Someone where wherever you get doubts, please ask checkbox. Okay, okay. If you have something important to ask, you can always write in chat box. I will try to answer it as and when suitable. Okay. So let's say I want to make an NMOS transistor. So this is how the microwind layout looks like. I believe it is visible to everyone. In case, please notify. If it is not visible, then notify. Uh, are you not? Are you able to see the microwind screen? Okay, hold on. No problem. I just share it. I believe now it should be visible. Okay. Okay. Great. Um, Great. Okay. So on the right hand side, you will find a palette screen. Okay. It might not be visible because palette is popping up as a separate window to me. So I can share only one window at a time. Okay. So if I just zoom in, so you see something like grid. Okay. You see yellow dots, right? So these yellow dot is nothing but the lambda grid. Okay. So let me draw something. I take the end diffusion layer and draw a block. Okay. Something like this rectangle. Okay. Now there is an option of 2D cross section. So I just click on this and draw a 2D cross section. So this is how it shows me that this is a p-type substrate. Okay. And the gray one on the bottom side. And on top of it, this is a green body, which is an N-type diffusion. If you look on the three-dimensional view, so this is how it should look like. Okay, I have to access this. Yeah. So you see this? This is the p-type substrate. This one. Okay, the gray body, and in the middle you have this. The green one is the diffusion, which is diffused. It goes inside the layer. Okay. So you see that I have just drawn a block, a simple rectangle. Okay. Then what? So I take one metal layer and draw something on the sides, something like this. and maybe something like this. Okay, that's it. Now if I go for a 3D view, so can you see this one, a 3D structure? And I just look at this. Yeah, so you are able to see this 3D structure. I see that. So this is end diffusion, and on top of it there's a metal layer, but they are not connected. You can see that they are not connected. It's just like something floating in the air. Now if I just take and short a contact between the end diffusion and the metal layer, okay, so it comes something like in between. Now if I click on the 3D view, which is on the top side menu bar, so you see something like this is connected. So this vertical line shows that this is the contact or the via between the 2 points. Okay, and same I can do here. I can just right click and say connect layers, so it just joins the end diffusion with the metal layer. So you see this vertical block or the building that indicates that this metal layer is connected to the end diffusion. Okay, now what I do, I take the polysilicon layer and draw something in between of some two blocks. So this is 2 lambda. You see this? This is 2 lambda. I made this of, I made this red block of 2 lambda in length. Okay. So if you see in 3D, this is how it look like. So it separates the drain and source diffusion. I just zoom a little bit. Yeah. So it separates the drain and source, and there is a channel formation beneath the gate material. You see this? So there is a channel formation between the gate, and it isolates or separates the drain and source. Okay, so this is a simple NMOS transistor. So if you look the top view, this is how it will look like. You see this one? So this is the same kind of view we are looking in my PPT also. Okay, so you have a red body which is polysilicon on the gate material. The green color is used for the n-type diffusion material. Okay, just simply remember that green N, so N for N diffusion, that's it. And blue colors or the various shades of blue, they are used for the various metal layers. Every software has little bit of different shade based on the developer's perspective, but mostly they are blue. Okay, so this is our NMOS transistor. That's it. This is simply a basic NMOS transistor. And you saw that I had just made few rectangles. They were not complicated. This is a very basic shape. Anyone learns in maybe junior KG or maybe senior KG, and you just draw square out of it or rectangle out of it, and this is what you can make in Microwind. Okay. So basically, this is how NMOS looks like. So I just share back my PPT. I believe I'm back in my PPT and everyone can see my PPT. So, hmm, a bit louder. Okay, I be try to be a bit louder. Maybe I just hold it in my hand. Okay. Okay. So I believe everyone can see the PPT back again. Yes. Okay. So here do you see that that is nothing but an NMOS transistor. That the same thing we have drawn just now. So you can just draw a metal block like this and a green block to indicate this may be the green block. Oh, sorry. I just, this is what the green block we made, green block for the end diffusion. And this was a metal block we made for the metal layers. And this was a polysilicon block in between we made for the polysilicon gate material. Okay. So these are nothing but you see that these are dimensions. Okay. Because you might ask, okay, किस साइज का ट्रांजिस्टर बनाना है वो ब्लॉक कितना बड़ा होना चाहिए what should be the length of the diffusion and what should be the width of the diffusion and what should be the width of the metal. So these are nothing but the dimensions given by the manufacturer. okay, or the designer, both. It's from the both. So it is like 2 lambda. So 2 lambda is minimum. If this is mentioning 2, so 2 is the lambda, because you remember we made lambda was half of the technology, right? Tech, lambda is half of the technology, so that means the gate length would be always 2 lambda. That is the minimum value you can have. This is minimum, remember this. So if I ask you, uh, what is the maximum size of gate length I can have? This is length, huh? This is length. So if this is 2 lambda, so that is equal to the length of the transistor. Sorry, that is the length of the transistor. Then there would be the width of the transistor. So width is how much? So this one, width of the diffusion, that is 6 lambda. Okay, these are the minimum values. These is the minimum values. Now if I ask you, what is the maximum value of width and length I can have? If I ask you a simple question, what is the maximum size of width and length of the transistor I can have? So can I have a quick 5 minutes poll? Can I get some answers? Just to know the opinion of the common thinkers. I believe everyone has got the question. I have mentioned that yes, we can design a transistor and MOSFET, and this is the minimum values of the MOSFET, that 2 lambda should be the minimum size of the length. So length should be minimum 2 lambda, and the width should be at least 6 lambda. Okay, this is the minimum value. So what is the max value I can have of the width and length? Width and length both. The maximum value I can have 4, 3, 10. Don't make a Fibonacci series. Okay, let me have few more. So what is the maximum value you can have? Lambda is equal to technology value. Lambda is equal to 10. Okay, anything else? Okay, anything as per requirement. That's I believe that's a good answer. Anything as per requirement. Yes, maximum is there is no limit. Maximum there is no limit. It's just like having a good salary. So it's just like, okay, to survive you have to, let's say for example, you have to earn at least maybe a 5,000 rupees a month. Okay, I know this figure may be 40 years back, but still, let's say for a minimum survival you require at least 5,000 rupees a month. This is the minimum value. Then what is the maximum value of it? That how much maximum you should earn in a month? Is there any upper cap? No, there is nothing. Okay, so the sky is the limit, or the space is the limit, if we talk about Elon Musk. Okay, so the maximum value depends that you have a big wafer, so you can make one transistor out of this big wafer, so there is no limit to it. Banao itna bada kaun mana karta hai? So if you can afford it and the design needs it, otherwise not. Okay, but you are trying to make things smaller so that you can fit more number of transistors. Okay, but then why smaller has a limit? हम इसको और छोटा क्यों नहीं कर सकते? ये 6 ही क्यों? I mean, other question is there. Be inquisitive. Huh? You can ask all such kind of question, that why there is 6? Why not 5? If I ask this question that ठीक है ये 6 क्यों है, 5 क्यों नहीं है, और ये value क्या है? ये value है width of the metal. Okay, and what is this 3? The 3 is the spacing between the polysilicon and the contact. So that is 3 lambda. So why it is 3 lambda? Why it is not 2 lambda? Why I can't keep it 2 lambda? Or why I can't keep it 4 lambda, which is much more safer value, isn't it? And why it is 2? Why can't I set my lambda as 1/4 of the technology rule file? Are you getting the question? Why can't I set that 1/4 of the technology file? Okay, why I can't do that? Yes, you can do that at least, but it is a grid. But let's say why it is 2 lambda. So the minimum value comes from the fabricators. Okay, the minimum value comes from the fabricator. It is like okay, how I put an example. Okay, maybe he's constructing yeah, a contractor is making a home for you. Okay, and in the design rule books it is mentioned that if you are making any house, okay, so the wall thickness which is there, wall thickness should be at least of 1 feet. Okay, isn't it? So that is the minimum wall thickness you should have to support a home, right? Yes, PDKs, yes, right. So if you do not keep 1 feet, probably the house may collapse, because someday if something goes wrong it may collapse. So to be a safer design methods, the fabricator has found out that the 4 is the minimum amount of thickness I should have of the metal so that it can fabricate. Then the spacing between this the gate and the wire should be 3, otherwise they may get shorted after the chemical processes. Okay, so if you keep 3, anything above 3, then there won't be any problem, but it is less than 3, then there would be high possibility of shortage. Okay, I mean shortage not be by degree, I mean shortage means like short circuit. Okay, so that's why you try to follow and adhere the design rules. Okay, these are nothing but the design rules. Okay, so this is how a layout look like of an CMOS inverter. So your schematic, sorry, I mean I have to, yeah, sorry, why, what is happening? Okay, why my pen is not working? Yeah, so your schematic is converted to an layout. Okay, we will make it, don't worry. So NMOS PMOS based, both will make this inverter. So these are called as design. They are set of rules and regulation which a designer needs to follow. I will be just introducing about the concept of design rule, and there are some basic design rules, lambda based rules, interconnect supply rules, and wires, antenna ratios, ESD protection rules. There are so many number of rules to be followed to make a successful design, and it's good to follow the rules. Okay, and so as the English language states, what are rules? Rules are the guidelines which anyone should follow to get a successful result out of the process you're following. Okay, so same is with these rules, that if you follow them, then you get a higher probability of success. If you try to violate it, then probably that will be wrong. It's just like on our roads we follow the traffic rules. So the traffic rules mention that you should not jump a signal, or you should not drive in the one way, otherwise there might be high chances of accident. But for example, your friend was injured and you see an hospital just 100 meters away but in the wrong way or the one way direction, and after one signal which is red, so do you think you will really follow the rules of the traffic at that moment of time? No, you will try to break up the rules and try to get your friend to the hospital as soon as possible. So the rules are there for the standard purpose, but a good designer is allowed to violate the rule by his gut feel and experience, and probably sometimes the design requirement. Okay, so I will be just talking about the design, some rules that okay, what significance it makes. For example, you have some chipset and there are millions and millions of transistors, and let's say that it's just consuming 100 watt of uh, power at 1 volt. Okay, or maybe let's say 2 volt. Okay, it's working on 2 volt, and the power is 100 watt. So can you let me know the current, how much current would be? Almost 50 amperes at the peak. Now imagine that 50 amperes of current, how would it be going inside? It will be passed through the various metal layers, okay? And it will be entering on one side and exiting on the other side, okay? So this is how that amount of current would be passed to the other ones. So if someone makes a thin track carrying that amount of current, okay, so you can imagine what may happen. It will burn off. It will burn off very easily. So it's better to have a thicker track, knowing the size of the or the amount of current that track is carrying. Okay, and at the same time, you also have to take care of the thermal effects on the chipset, because if that track is carrying the current for long period of time, So what will happen? It'll heat up, and there should be, natural heat dissipation method should be designed. So what designers do, they put slots in between the tracks so that the more number of surface corners the track has, the better is the heat dissipation, okay, or the transmission. And other rules, like there are many such, so many rules, there are hundreds and hundreds and hundreds of rules. I'm just covering a couple of them. For example, supply design rules. So you have two metal tracks, which is one like this and another goes like this. So it's 90-degree turn, and probably you're changing the layer also. This is maybe layer one and this is on layer two, and you're trying to join them. Now I can just put one wire over here. So what will happen? Electrically it is okay. Okay, there won't be any electrical issues in my design. I can simulate the design because my software, the simulator, might not know that there's only one wire which is connected through metal tracks, and probably this metal is also that thick enough to carry that amount of current load. But the designer has kept only one wire in between the contact. So what may happen, someday this wire may broke and it may fail. So that would be unreliable. So more the wires you put on the cross section of the two layers, better the design is. So more the wires, better the design. Okay. So similarly, there are so many rules which you can cover through. I mean, like basically design rules are there to just make sure that your design will work properly after the fabrication. Okay. And more the rules you violate, and the better the chances you get of failures. Simple as that. Okay. So we just quickly talk about power consumption. I will make sure that we cover at least some time of designing something. Today I will stop the theory maybe after the power consumption, and we will get into hands-on. Okay. So uh, power consumption. Why to worry about power? Uh, I believe we are all familiar that why power consumption is very important. And these days we cannot live without gadgets, and the gadgets operate with batteries most of the time. And if they are drawing huge amount of power out of it and they are not able to work more than a couple of hours, then probably the product will not be a success. So let's find out, okay, in CMOS transistors, where does the power is being drawn? Okay, so it is being drawn by dynamic power consumption. Okay, that is the essential transition. Okay, I believe everyone is familiar with dynamic power consumption. That is like because if there is any driver and he's trying to charge any capacitor, which is like capacitance. Okay, so what happens? Like you put some current into it. Okay, so it charges, and also you discharge the current so that it comes down to low level. So you consume, for each transition you consume an half CV square of current to charge and discharge the capacitor. So what happens when you are giving any input like this? So in this case, rising falling, you are charging and discharging the uh, capacitor. Okay, so that is required because that is essential power consumption. It's just like you want to work for the day. I mean, you work on some factory and you there is a labor intensive job, and just hold on a second. Someone is trying to. Okay, so you are trying to work out in a factory, and for the entire day you are working in and out. So what will happen? You will burn out energy, you will burn out the calories. Okay, so what do? You eat food for the energy. So that is essential because you have to work out for the daily. Okay, isn't it? So, and this is called as dynamic power consumption. Okay, and then there is a short circuit power current. Okay, short circuit is that when for the momentary the CMOS circuit, they get shorted to each other. Okay, and there is a direct path between the supply rails where the current pass through. I will explain that in the coming slide. uh, uh, is everyone familiar with the glitches? uh, Maybe couple of yes or no will work. Okay, 50-50, one yes, one no. No, nah, no, nah. Okay, fine. No problem. No problem. No problem. I just cover it. Glitches. Okay. Glitches are glitches. Okay. We talked about that, and human requires 2000 calories. 2000 calories in a day to work. So that means that is the energy he's consuming for the factory work, because he's working in a factory और दिन भर बैठ के वो काम करता है, and he's doing essentially that energy requirement is there. But what happens when you're sitting with your friends in the factory and you're just chatting around? So that is actually glitch, which is because this was not expected from you, and you do it because of fun and the wastage of time. So let's assume that this is some circuit, and the output was expected to go logic 1. Okay, any change in the input, there was some change. Let's say it was 0, 1 1 0, and it was 1 1 1, something like this. Okay, or sorry, I cannot draw that area. Okay, so the output was expected to go something like this. Okay, but instead of that, the output goes like this. Now what is that? That is nothing but a glitch. So glitch is an short spike, small spike at the output produced by the circuit, improper balance delays, and it is just a spike. It may or may not harm your design output. 90% of the time they do not harm your design outputs, because designs, they are made in such a manner that the glitches will not damage your technical output. It's just like in the lunch time of the factory, you are sleeping so that you conserve your energy, but instead of that, you just go and play football in the factory. So what is happening? Instead of working in the factory, you are spending your extra energy in football playing. I agree that football is a great game and you should all play for the fitness, and the guy is also doing that. But instead of conserving his energy, he's wasting the energy in the playtime. Okay, so that is a kind of glitch. Okay, it may or may not harm his performance. He may work in the factory also, right? But then he's wasting extra. Okay, so glitches, they may not harm your output, but understand that they are wasting a huge amount of power consumption. Okay, so that's why the glitches are serious sometimes. Then another problem is leakage. Okay, uh, leakage. You guys understand leakage? Uh, Leakage in diode. Uh, okay, let me draw it for you. You you remember this graph? Sorry, man. This is the VI characteristics of the diode. You remember this? Yep. Okay. So do you remember this part? Yes. Okay. I am getting a lot of yes. Okay, yes, sir, we remember it. So let me know if this, my drawing is correct or not. Tell me if this graph is correct or not. Is this graph correct? Okay. Just remember that this is a graph number 1. Okay. This is graph number 1. Let me draw again. This is the graph number 2. Which one is correct? Okay, okay, I get it. So most of the people remember very good. So yes, this is leakage because this guy is I. This is the current. So when you are operating the diode in the reverse bias, okay. So the diode leaks some amount of current. Okay, so this is called as leakage current of the diode. Although this is very small, maybe like if I put the smallest figures like 1 microamperes, only 1 microampere. It's a small value. क्या है? कुछ भी नहीं है. Peanuts. isn't it? But then every transistor leaks. They leak current when they are not operating, or when they are not switching. Okay, so this is called as leakage current. And generally the leakage is this generation problem. This is a question of debate or discussion. It's very good to understand how the leakage became of primary concern for the chip designers. Because 20 years back, the designers were not talking about leakage current. They were least bothered about leakage current and the performance of the leakage of the transistors. And but these days, it is the most important factor for the designers. Very, very important. Okay, and the question comes up, why and how the leakage became so important. Okay, it's just like child marriage and other issues in the society. It is almost the similar, because everyone is familiar with water conservation. You must have seen a lot of advertisements by the government or some local NGO, or in the neighborhood, posters everywhere. People talk about that, don't waste water, jal hai to jeevan hai, jal hai to kal hai, or pani bachao, pani bachao, pani bachao, right? Now you tell me that why it has become so serious, and this is what we are talking about today. You just go and ask your parents that, did they saw such kind of advertisement 40 years back or 30 years back in their life? I mean, during their teenage or during their adulthood, did they saw such kind of advertisement? Probably they will say no, no. So why water conservation all of a sudden has become such a important? That is because the population. Look at our population. We have gone exponentially. The kind of we were 0.01 billion during the independence, and we are now 1 billion plus. So obviously, uh, the requirement of water is huge. So saving every drop matters. Okay, and the same with the chipsets. So in 20 years back, the chips were having hardly few millions of number of transistors. So even though they leak 1 microampere, so you will have only what, like 1 ampere of current was leaked, you see. Because let's say one transistor leaks 1 microampere of current, just for the sake of figure. So if you have 10 to the power 6 transistors, okay, so how much current would be leaked? Okay, so that will be almost 1 ampere of current would be leaked. Maybe you're not bothered about, ठीक है, मेरे पास बहुत है current, ठीक है. But this was 1 million. This is 1 million transistors. Now you have 1 billion transistors. Now what? Imagine the figures. You understood? So if all the transistors are leaking in 20 years back design, the leakage was 1 ampere. Probably you can handle it. But imagine the number of transistors you have today, and 1 billion. I'm putting at the lowest figures. This figure has been surpassed a few years back. Okay, so you can imagine the amount of current the devices will leak, isn't it? So your batteries of the devices will discharge in a flash. So that's why it is this generation problem. You have to think of conserving power. Okay, now let's have a quick view that how the power consumption. So if this is a CMOS circuit, so what happens when you give a zero input? So what happens? The PMOS is on and the NMOS is off. So your output VDD is charging this capacitor, okay, to a logic high value. Okay, you will get a logical high. And when you give a logic high at the input, that is 1 at the input, so it becomes reverse, that the PMOS turns off and NMOS turns on, and the output discharges to the ground, and you get a logic low output. But if your inputs are sloppy, something like this, so during this, what happens? Rise and fall times, both are on for a moment here, just for a moment. How long? It is only for this duration, and this is a very short duration, but at least they would be turned on. And when they would be short circuit, you will get spikes in the current. Okay, and that will be an huge short circuit power dissipation. And the leakage is that when they are in reverse bias, so obviously they are leaking current. Then glitches. These days they have become a big concern to the designers, because glitches they occur because of the differential paths, delay paths, that you have some circuits and they have differential delay. This guy has a 0 delay and this guy has a 2 delay. So obviously if you change the input same time at the input side, this guy will reach earlier and this guy will reach late. So the response of this guy would be different. So probably you were expecting something like this output, but you will get something like this. Okay, so this guy is a glitch. This guy is a glitch. Okay, so this, it is not appreciated. And you imagine that if even the 30% of the transistors are producing glitches, so you can imagine that the glitches will be wasting a huge amount of power. Okay. Okay, I believe everyone is familiar with this basic formula, that the energy is half cv square of charging and discharging of the capacitor. And as you are doing f times in a circuit, so the power consumption would be half cv square. Okay, twice in the frequency, right? So that gets cancelled and you get fcv square, the power consumption. Okay, so that means your uh, the power consumption is dependent on capacitance, the voltage supply, and the frequency, capacitance or resistance. Okay, so is this clear? uh, mm, fcv square. Okay, so capacitance means what? Is it the load capacitance of the driver? Actually, yes, but then the capacitance over here is talked as a collective capacitance value of the entire circuit. Entire circuit. If you have 1 million transistors, let's say 1 million transistors, okay, so the how much amount of capacitance the total circuit has, okay, and it is operating at a particular voltage, and it is operating at a particular frequency. So based on this factor, you can calculate the power consumption in the given circuit. Okay, so how do you reduce power? That we will talk on it. So generally, if you talk about any microprocessor, you will see that the cycle also, because they are working at the highest speed possible. Many people say that the IO lines are huge power hungry units, whereas these are the least ones because they are not updated on every clock cycles. They are updated after 100 clock cycles or 200 clock cycles or 50 clock cycles like this. So they don't get updated that frequently. Okay, and other part also consume a very less amount of it as compared to the clocks. Okay, they consume huge amount of power. That's why in every chip design teams there is separate couple of people or expertise are there who are only specialized in designing a very good clock network. Okay, so how do we work on saving power? There are a lot of literature available, lot of, because I can't say that okay, this technique is best for everyone or this thing will work for everyone. No, there are various technologies and various methods which people apply on reducing the power consumption. Okay, uh, so if I ask you voltage, can we change voltage? Because you see, because if you see the formula, you remember the formula, right? So there are three factors: F, C, and V. So किसको कम करें? Shall we reduce voltage? Okay, how many will say that yes, we can reduce voltage? Can I have a quick poll for all three components? How many people says that yes, voltage can be reduced? Probably I've shown the answer that, so no one is coming forward. Okay, so yes, voltage can be reduced.
Okay, but remember you have already designed the tube lights. The tube light will work at 220 or 240 volt only. So you cannot redesign the tube light. You have to entirely redesign the tube light for another voltage, isn't it? So you can't reduce the voltage. Not every time. You know, it's just before the design you have to think that I will work at what voltage, what technology, because voltage is dependent on the technology transistor you're using. Okay, lower the technology, lower the voltage would be. Okay, then what? Capacitance को कम कर दो. How many of you are using Nokia 1110 phone? You remember this phone? Is anyone in the group who's using the basic feature phone? Nokia 6600. Who is this? Looks like a old guy, huh? Because as far as I remember, Nokia 6600 came way back in late 90s, I believe. Anyhow, I don't think so. Anyone would be using a basic feature phone, right? Okay, why? It works for the battery. You charge the battery once, and it goes for 1 week, isn't it? Do you use it? No. Why? Although it has low power consumption. Why? Because it is not having enough C. C means features. More the transistors, more the feature, isn't it? And the better is the sellability. You imagine, you are trying to get a Snapdragon 855 chipset. Then I offer you that I have a Snapdragon 825 chipset. So there are two chipsets. Okay, you have Snapdragon 825 and a Snapdragon 855. So what is difference? Capacitance. Capacitance not exactly means in microfarads, but actually the number of transistors and the number of features both of them are offering. This guy has more number of transistors and more features, more faster, having higher performance and everything good functions. So that is because this guy is having more number of transistors, and hence the C will also be higher. But at the same time, the power factor is also higher of this guy, and iska power factor is lower as compared to this guy, isn't it? So if you reduce C, that means you are reducing number of transistors and you're reducing the features of the product, and probably no one will like your product. You won't be able to sell it, or probably you have to position your product like that way. Okay. So the last